Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The 9th century presented a unique landscape for scientific inquiry, particularly within the realms of astronomy and mathematics. Scholars of the era grappled with a legacy of ancient knowledge, most notably inherited from Hellenistic Greece and India, while simultaneously striving to refine, correct and expand upon it. Astronomical observation, though a practice dating back millennia, still suffered from limitations in instrumentation and computational techniques. Existing astronomical tables, such as those found within Ptolemy's Almagest, served as foundational texts, yet their inherent inaccuracies became increasingly apparent as observational data accumulated. These discrepancies posed a significant challenge to astronomers attempting to develop accurate models of celestial motion and to predict astronomical events with precision. The need for more refined methodologies and more precise mathematical tools was palpable. It is within this context that Muhammad ibn Jabir al-Harrani al-Battani, later known in the Latin West as al-Battanius, emerges as a pivotal figure. Al-Battani was a transformative scholar whose work revolutionized the field of trigonometry and ushered in a new era of astronomical observation and calculation. His contributions were characterized by a rigorous commitment to empirical observation, coupled with a profound understanding of mathematical principles. He sought to reconcile theoretical models with observed reality, pushing the boundaries of astronomical knowledge and establishing a standard of accuracy that would influence generations of scientists to come. Al-Battani's journey began in Haran, a city in Upper Mesopotamia, a region known for its rich intellectual heritage. Haran, even after the decline of its overtly pagan identity, remained a center of learning where ancient Greek and Babylonian traditions mingled with emerging Islamic scholarship. Born around 858 CE, al-Battani received his early education in this vibrant environment, likely benefiting from the accumulated wisdom of generations of scholars who had preserved and translated classical texts. The city's history as a hub of astronomical and mathematical knowledge undoubtedly shaped al-Battani's intellectual trajectory, fostering a deep appreciation for both theoretical frameworks and empirical investigation. His family, it is believed, were members of the Sabian sect, whose religious practices involved star worship, so it is perhaps little surprise that al-Battani found himself drawn to the study of the heavens. Early in his career, al-Battani recognized the shortcomings of existing astronomical knowledge. He meticulously examined the astronomical tables available to him, comparing their predictions with his own observations of the celestial sphere. This process revealed significant discrepancies, particularly in the predicted positions of the sun, moon, and planets. Ptolemy's model, while groundbreaking for its time, relied on a geocentric view of the universe and employed geometric constructs, such as epicycles and difference, to explain the observed motions of celestial bodies. These constructs, however, were approximations that introduced errors into astronomical calculations. Al-Battani sought to address these errors through a combination of improved observational techniques and more sophisticated mathematical models. The problems al-Battani confronted were not simply academic exercises. They had practical implications as well. Accurate astronomical data was essential for a variety of purposes, including timekeeping, navigation, and the determination of religious observances, such as the timing of prayers and the determination of the Qibla, the direction of Mecca. Existing methods often yielded inaccurate results, leading to inconsistencies and disputes within the Muslim community. Al-Battani's work, therefore, had the potential to address both theoretical and practical needs, contributing to a more accurate understanding of the cosmos and facilitating more precise applications of astronomical knowledge in daily life. One critical area of focus for al-Battani was the development of more accurate methods for determining the fundamental parameters of the solar system. He recognized that the values used for quantities such as the obliquity of the ecliptic, the eccentricity of the sun's orbit, and the length of the year were subject to error. These parameters served as the foundation for all astronomical calculations, so any inaccuracies in their values would propagate throughout the entire system, leading to further discrepancies between theory and observation. Al-Battani embarked on a program of meticulous observation and careful calculation, using newly developed instruments and techniques to refine these fundamental parameters. Another significant challenge al-Battani addressed was the inherent complexity of Ptolemaic astronomy. Ptolemy's model, while mathematically sophisticated, involved a complex system of interlocking circles and eccentric motions. These geometric constructs made calculations cumbersome and time-consuming, requiring a high degree of mathematical skill and attention to detail. Al-Battani sought to simplify these calculations through the introduction of new mathematical tools, most notably the use of trigonometric functions. He recognized that trigonometric functions, such as sine, cosine, and tangent, could provide a more elegant and efficient means of representing angles and distances in astronomical calculations. By replacing the cumbersome geometric methods of Ptolemy with trigonometric functions, al-Battani streamlined the process of astronomical calculation and made it more accessible to a wider range of scholars. Al-Battani's initial work laid the groundwork for his later groundbreaking contributions to both trigonometry and astronomy. He identified the critical problems hindering accurate astronomical prediction and began developing the tools and techniques necessary to overcome these limitations. His commitment to empirical observation, coupled with his deep understanding of mathematics, set him apart as a true innovator in the field. The stage was set for a series of remarkable discoveries and innovations that would transform the landscape of astronomical and mathematical knowledge. Al-Battani's embrace of trigonometric functions marked a pivotal moment in the history of mathematics and astronomy. Prior to his work, astronomers relied heavily on the geometric methods outlined in Ptolemy's Almagest, which primarily utilized chords to represent angles and distances. While effective, these methods were often cumbersome and computationally intensive, particularly when dealing with complex astronomical calculations. Al-Battani recognized the inherent limitations of this approach and sought a more streamlined and versatile system. The shift from chords to sines, cosines, and other trigonometric functions was anything but a simple substitution. It represented a fundamental change in how angles and their relationships to lines and curves were conceptualized and manipulated. Chords, defined as the straight line connecting 2 points on a circle, were geometrically intuitive, yet lacked the algebraic properties necessary for efficient calculation. Trigonometric functions, on the other hand, provided a direct algebraic link between angles and ratios of sides in right triangles. This algebraic representation unlocked a wealth of new possibilities for simplifying calculations and developing new mathematical tools. One of the key advantages of using trigonometric functions was their ability to be easily manipulated using algebraic identities. Al-Battani developed a comprehensive set of these identities, which allowed him to transform complex trigonometric expressions into simpler, more manageable forms. These identities proved invaluable in solving a wide range of astronomical problems, such as determining the positions of celestial bodies, calculating the distances between them, and predicting the timing of astronomical events. For instance, Consider the problem of determining the altitude of a star above the horizon at a given time and location. Using Ptolemy's method of chords, this calculation would involve a series of geometric constructions and measurements, often requiring the use of complex tables and interpolation techniques. Al-Battani, however, could use trigonometric identities to express the altitude of the star directly in terms of its declination, right ascension, and the observer's latitude. This algebraic formulation greatly simplified the calculation and reduced the potential for errors. Al-Battani's innovative work extended beyond the development of trigonometric identities. He recognized the need for accurate and readily available trigonometric tables, which would allow astronomers to perform calculations quickly and efficiently. He meticulously constructed these tables, calculating the values of sine, cosine, tangent, and cotangent for angles at small intervals. The precision of his tables far surpassed those of his predecessors, enabling more accurate astronomical predictions. The creation of these trigonometric tables was a monumental undertaking, requiring immense computational effort and a deep understanding of numerical methods. Al-Battani employed sophisticated techniques to approximate the values of trigonometric functions to a high degree of accuracy. His tables became an indispensable tool for astronomers and surveyors for centuries to come, facilitating advancements in both theoretical and practical applications. Moreover, al-Battani made significant contributions to the field of spherical trigonometry. Spherical trigonometry deals with the relationships between angles and sides of spherical triangles, which are triangles drawn on the surface of a sphere. This branch of mathematics is essential for solving problems in astronomy, navigation and surveying, where the curvature of the Earth or the celestial sphere cannot be ignored. Al-Battani developed a number of important theorems and formulas in spherical trigonometry, which allowed astronomers to solve problems that were previously intractable. For example, he provided a general solution to the problem of finding the direction of Mecca from any given location on Earth, a crucial task for Muslims performing their daily prayers. His work on spherical trigonometry laid the foundation for future advancements in this field and had a lasting impact on the development of cartography and navigation. The problems that existed before al-Battani's innovations stemmed from the limitations of relying solely on geometric methods and the inherent difficulty in performing complex calculations using chords. Ptolemy's Almagest, while a monumental achievement, presented a system that was often cumbersome and prone to errors, especially when applied to practical astronomical problems. Al-Battani's solutions were uniquely suited to overcoming these limitations by providing a more algebraic, efficient, and accurate framework for astronomical calculations. His introduction of trigonometric functions, development of trigonometric identities, creation of precise trigonometric tables, and contributions to spherical trigonometry collectively transformed the landscape of mathematical astronomy. These innovations not only simplified existing calculations, but also opened up new avenues for research and discovery. Al-Battani's work empowered astronomers to make more accurate predictions, refine their understanding of the cosmos, and develop new technologies for observing and measuring the heavens. The mathematical significance of his work lies in its ability to bridge the gap between geometry and algebra, providing a powerful set of tools for solving a wide range of scientific and practical problems. His legacy continues to inspire mathematicians and scientists to seek elegant and efficient solutions to complex challenges. Al-Battani's profound impact on astronomy stems not only from his mathematical prowess, but also from his dedication to meticulous observation. He sought to refine and correct existing astronomical models, particularly those presented in Ptolemy's Almagest, through careful measurements of celestial phenomena. These observations, conducted over decades, provided a wealth of new data that challenged established theories and paved the way for a more accurate understanding of the cosmos. One of al-Battani's most significant achievements was his precise determination of the length of the solar year. Ptolemy had estimated the solar year to be 365 days, 5 hours, 55 minutes, and 12 seconds. Al-Battani, using his own observations and sophisticated calculations, arrived at a value of 365 days, 5 hours, 46 minutes, and 24 seconds. This was remarkably close to the modern value and represented a significant improvement over Ptolemy's estimate. The accuracy of this measurement had profound implications for calendar keeping and the prediction of seasonal events. Another key area of focus for al-Battani was the obliquity of the ecliptic, which is the angle between the Earth's equator and the plane of its orbit around the Sun. Ptolemy had assumed this angle to be constant, but al-Battani's observations revealed that it was actually decreasing over time. He determined the obliquity to be 23 degrees and 35 minutes, which was more accurate than Ptolemy's value and provided evidence for the gradual change in this fundamental astronomical parameter. This discovery demonstrated the dynamic nature of the celestial sphere and highlighted the need for continuous observation and refinement of astronomical models. Al-Battani also made important contributions to understanding the motion of the Sun. He carefully observed the position of the solar apogee, which is the point in the Sun's orbit where it is farthest from the Earth. Ptolemy had fixed the position of the apogee, but al-Battani's observations showed that it was slowly moving over time. He determined the rate of this movement and incorporated it into his astronomical tables, allowing for more accurate predictions of the Sun's position. This correction was crucial for improving the accuracy of astrological forecasts and for understanding the complex dynamics of the solar system. The meticulous observations of solar and lunar eclipses formed an integral part of al-Battani's astronomical work. By carefully recording the times, durations, and magnitudes of these events, he was able to refine his measurements of the length of the year and other astronomical parameters. These observations provided independent confirmation of his earlier findings and helped to solidify his reputation as one of the most accurate astronomers of his time. Furthermore, his eclipse data was invaluable for later astronomers who sought to reconstruct the history of celestial events and to test the validity of their own astronomical models. Al-Battani's corrections to Ptolemy's Almagest addressed several key problems in predictive astronomy. Ptolemy's model, while groundbreaking for its time, contained inaccuracies that led to errors in the prediction of planetary positions and other celestial phenomena. Al-Battani's improved measurements of the solar year, the obliquity of the ecliptic, and the position of the solar apogee, when incorporated into astronomical calculations, significantly reduced these errors. This resulted in more accurate predictions of eclipses, planetary conjunctions, and other astronomical events, which had important implications for practical applications such as navigation, timekeeping, and agriculture. The methods al-Battani used for his observations were a testament to his ingenuity and skill. He employed a variety of astronomical instruments, including astrolabes, quadrants, and sundials, to measure the positions of stars and planets. He also developed new techniques for using these instruments, which allowed him to achieve greater accuracy than his predecessors. For example, he devised a method for determining the altitude of the Sun at any time of day, which was essential for calculating the time of prayer. His meticulous approach to observation and measurement set a new standard for astronomical research and inspired later generations of scientists to adopt similar methods. A cornerstone of al-Battani's legacy is his Kitāb az-Zīj, or the Book of Astronomical Tables. This comprehensive astronomical handbook was the culmination of his years of research and observation. It contained a wealth of information on a wide range of astronomical topics, including tables of the positions of the Sun, Moon, and planets, as well as detailed explanations of how to use these tables for astronomical calculations. The Kitāb az-Zīj was a remarkable achievement in its own right, but its importance was further enhanced by the fact that it incorporated al-Battani's many corrections to Ptolemy's Almagest. This made it an indispensable resource for astronomers throughout the Islamic world and beyond. The Kitāb az-Zīj included detailed trigonometric tables which were far more accurate and extensive than those available in Ptolemy's time. These tables, based on al-Battani's own calculations, allowed astronomers to solve a wide range of astronomical problems with greater precision. The book also contained detailed instructions on how to use trigonometric functions to calculate the distances and angles between celestial objects. This made it an invaluable tool for surveyors, navigators, and other professionals who needed to perform accurate measurements of the Earth and the sky. Furthermore, the Kitāb az-Zīj presented al-Battani's innovative methods for solving astronomical problems using algebraic techniques. He demonstrated how to use equations to calculate the positions of the Sun, Moon, and planets, as well as to predict eclipses and other celestial events. This algebraic approach to astronomy was a significant departure from the geometric methods used by Ptolemy and other earlier astronomers. It paved the way for a more analytical and quantitative approach to the study of the cosmos. The importance of the Kitāb az-Zīj as a comprehensive astronomical handbook cannot be overstated. It served as a standard reference work for astronomers for centuries, both in the Islamic world and in Europe. Its tables and methods were widely used for practical applications such as navigation, timekeeping, and calendar making. The book was also a major source of inspiration for later astronomers who sought to refine and improve existing astronomical models. Al-Battani's Kitāb az-Zīj stands as a testament to his intellectual curiosity, his dedication to precise observation, and his profound impact on the history of astronomy. It represents a pivotal moment in the development of astronomical knowledge and a bridge between the ancient world and the scientific revolution. Al-Battani's analytical approach to astronomy distinguished his work from the purely geometric models employed by Ptolemy and other earlier figures. His methods fostered a more quantitative investigation of the cosmos. This shift toward analytical techniques proved to be a lasting contribution, influencing generations of astronomers who followed. The Kitāb az-Zīj's significance as a comprehensive astronomical handbook resonated deeply across cultures and centuries. It functioned as a standard reference for astronomers spanning both the Islamic world and Europe. Its tables and methodologies found widespread application in practical domains, including navigation, precise timekeeping, and accurate calendar construction. Furthermore, the book provided a wellspring of inspiration for subsequent astronomers striving to refine and enhance prevailing astronomical models. Al-Battani's Kitāb az-Zīj embodies his intellectual engagement, his dedication to precise observational data, and his profound influence on the progression of astronomy. It marks a crucial juncture in the evolution of astronomical understanding, serving as a conduit connecting the ancient world to the burgeoning scientific revolution. The Kitāb az-Zīj did more than simply circulate, it actively shaped astronomical thought. Translations of the work into Latin made al-Battani's findings accessible to European scholars, sparking a wave of new investigations and reinterpretations. This transmission of knowledge played a pivotal role in the development of Western astronomy, particularly during the Renaissance. The influence of al-Battani can be seen in the works of many prominent astronomers, including those who spearheaded the Copernican revolution. One of the most significant aspects of al-Battani's legacy lies in the meticulous accuracy of his astronomical observations. He refined existing measurements of various celestial parameters, such as the length of the solar year, the obliquity of the ecliptic, and the position of the Sun's apogee. These refined values provided a more accurate foundation for astronomical calculations and contributed to a better understanding of the workings of the solar system. His commitment to precision set a new standard for astronomical observation and analysis. The translation of al-Battani's Kitāb az-Zīj into Latin, under the title De Scientia Stellarum, marks a pivotal moment in the transmission of scientific knowledge between cultures. This translation, carried out in the 12th century, provided European scholars with access to a wealth of astronomical data and techniques that had been developed and refined in the Islamic world. The Kitāb az-Zīj quickly became an indispensable resource for European astronomers, influencing their work for centuries to come. Nicholas Copernicus, whose heliocentric theory revolutionized astronomy, drew heavily upon the work of his predecessors, including al-Battani. Copernicus cited al-Battani's observations and calculations in his own groundbreaking treatise, De Revolutionibus Orbium Coelestium. Specifically, Copernicus relied on al-Battani's determination of the solar eccentricity and the position of the sun's apogee. This reliance demonstrates the direct influence of al-Battani on the development of Copernican astronomy. Tycho Brahe, renowned for his meticulous astronomical observations, also recognized the value of al-Battani's work. Brahe incorporated al-Battani's data into his own astronomical tables and used his methods to improve the accuracy of his measurements. Brahe's commitment to observational precision mirrored al-Battani's own dedication to accurate data, highlighting a shared commitment to empirical evidence. Johannes Kepler, who formulated the laws of planetary motion, likewise acknowledged the contributions of al-Battani. Kepler consulted al-Battani's Kitāb az-Zīj in his quest to understand the elliptical orbits of the planets. While Kepler ultimately departed from the circular orbits assumed by al-Battani, he nevertheless recognized the importance of al-Battani's observations and calculations. The influence of al-Battani extends beyond these prominent figures. Many other European astronomers and mathematicians studied and utilized his work, incorporating his findings into their own research. The Kitāb az-Zīj became a standard textbook in European universities, shaping the curriculum and training of future generations of astronomers. Al-Battani's methods for solving spherical triangles, for instance, were widely adopted and continue to be used in modern trigonometry. Beyond the direct influence on individual astronomers, al-Battani's work contributed to a broader shift in astronomical methodology. His emphasis on precise observation and mathematical analysis helped to move astronomy away from purely theoretical speculation and toward a more empirical and quantitative approach. This shift laid the groundwork for the scientific revolution, which emphasized the importance of observation, experimentation, and mathematical modeling. Al-Battani's contributions to trigonometry are particularly noteworthy. He developed new methods for solving trigonometric problems, including the use of sines, cosines, and tangents. He also produced accurate tables of trigonometric functions, which were essential for astronomical calculations. His work in trigonometry helped to transform it from a tool for astronomical calculations into a mathematical discipline in its own right. The enduring legacy of al-Battani lies in his commitment to precise observation, his mastery of mathematical techniques, and his ability to synthesize and refine existing astronomical knowledge. He stands as a towering figure in the history of astronomy, bridging the gap between the ancient world and the scientific revolution. His work continues to inspire scientists and mathematicians today, serving as a reminder of the importance of empirical evidence, mathematical rigor, and intellectual curiosity. In synthesizing al-Battani's key achievements, one recognizes his profound role in advancing both astronomical knowledge and mathematical techniques. His meticulous observations, particularly the refined measurements of fundamental astronomical parameters, established a new benchmark for accuracy. He improved our understanding of the solar year's length, the ecliptic's obliquity, and the sun's apogee position. Simultaneously, his contributions to trigonometry, including novel methods for solving trigonometric problems
and the creation of accurate trigonometric tables transformed the field into a more sophisticated mathematical discipline. His work acted as a crucial bridge, connecting the astronomical insights of ancient Greece with the burgeoning scientific revolution. The Kitāb az-Zīj, translated into Latin, transmitted a wealth of knowledge and techniques to European scholars, influencing figures like Copernicus, Brahe, and Kepler. This cross-cultural exchange fostered a more empirical and quantitative approach to astronomy, emphasizing observation, experimentation, and mathematical modeling. Al-Battani's dedication to precise observation and mathematical rigor laid the foundation for future scientific progress, confirming his lasting impact on the trajectory of scientific thought. His legacy serves as a testament to the power of intellectual curiosity and the pursuit of knowledge.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.